Good morning, everyone. Are you guys able to hear me? Yes. Okay, wonderful. I hope you're all having a great Wednesday morning. We have a little bit of a smaller class today, which is perfectly fine. We're going to be talking about chapter 13 today. I actually do want to test out really quickly if the volume on the video will work. So, let me see if this will work. Let's see. Okay, can you guys let me know if you can hear it?
Kind of what was always assumed or the status quo, while the alternative hypothesis, hey, there's news here. There's something alternative here. And to test it, and we're really testing the null hypothesis. We're going to decide whether we want.
Okay, perfect. So we can hear it. Okay, I know we had issues last time when I was trying to play a video. That's why I wanted to just quickly check to see if I had figured out my issue, my my technical difficulty there. So I'm glad that I was able to figure it out. Okay, so what time is it? It's 10:30. Perfect. Right on schedule. So let's go ahead and get started. Okay, so today we're going to be going over chapter 13, and this is going to be part 2. So use of statistics in infection prevention and control. There's going to be a lot of reading for these slides because the information needs to be delivered. And so, but there's still questions, so don't worry. So let's talk about rates and ratios utilized in epidemiology. So a rate measures the probability of occurrence, or for example, frequency, in a population of some particular event, such as cases of a disease or deaths. Epidemiologists use rates to summarize the experience of a population over time. A rate provides a means of comparing the occurrence of an event in one population to similar populations by adjusting for differences in population sizes. So some types of rate calculations include incidence rates, prevalence rates, point prevalence rates, and attack rates. Okay, this slide is backwards. We're supposed to go over the rate formula first. Okay, so the rate formula is going to be x divided by y times k. And this is going to be really important. The PowerPoint isn't showing up. Oh my goodness, Luce, you did it again. You did it again. Okay, what about now? Okay. All right, guys. So, yes. Okay. Let's continue with the rate. Okay, so the rate, this is the formula right here, x divided by y times k. So this is going to be really important when it comes to the questions that they're going to ask you on the test. So it's important for you to know the formula, so to remember x divided by y times k, but also for you to know exactly what each variable represents, right? So x is the numerator, which is going to equal the number of times the event or infections have occurred during a specified time interval. Y is the denominator, which equals a population, like the number of patients at risk from which those experiencing the event were derived during the same time interval. So Y, just remember the population at risk. K is a constant used to transform the results of a division into a smaller uniform quantity so that it can be compared with other similar quantities, right? So a lot of the times what they're going to utilize is 1,000. So the usual value selected for infection rates among patient or device days is 1,000, and this standardizes the rates for comparison purposes. So let's do a concept check. To calculate the catheter-associated urinary tract infections rate for a unit for 1 month, the denominator should be, so this is specifically asking you for the denominator. A, the number of patients for the unit for the month. B, the number of admissions for the unit for the month. C, the number of patients with urinary catheters for the month. And D, the number of urinary catheter insertions for the month. So it's asking us for our denominator, which would be y, right? So y is the denominator, which equals a population from which those experiencing the event were derived during the same time interval. So with that hint, it should really help to guide you towards the correct answer. Okay. So our population at risk when you're dealing with CAUTIs is going to be the number of patients with urinary catheters for the 1 month, right? Because if you don't have a catheter, you can't really be included as part of the CAUTI rates, right? So it's important not only to know the equation, but what those values mean, because if you know it's x divided by y times k, but you don't know where you need to plug in k or what x denotes, like it's going to be very difficult for you to be able to answer these questions. So remember, persons in the denominator must reflect the same population from which the numerator was taken. So if you're focusing on a specific unit, you can't pick people from a different unit. You can't pick people, that basically don't reflect that same population. Counts in the numerator and in the denominator should cover the same time period. So that's very important as well. And lastly, at least in theory, the persons in the denominator should have been at risk of the event or occurrence. Okay, so question 1. An IP collected the following data from the ICU for the month of March. How would she calculate the CAUTI rate for the month of March? And we're going to use rate equals x divided by y times k. So we need to know what x is, right? So the numerator is going to equal the number of times the event occurred. So like the infection or event has occurred. We just went over what y is, right? And then k is going to be our constant. And the usual value for k is going to be 1,000. So this should help to guide you in what the correct answer should be. So remember, yeah, we have this formula here, but you need to know what these values stand for. Let's see, we have everyone put B, which is the correct answer, but I'm guiding right now, right? So I'm helping you by reminding you what each of those values mean. What I want you to keep in mind is when you're studying and when you're taking your quiz questions, when it's time for you to take your CIC exam, Luce isn't going to be there to remind you what X or what Y or what K should be. So making sure that you're trying your best to not only memorize it, but to really try to understand how to utilize these equations or these formulas that they're giving you so that you're able to apply them to their questions. Okay, so our different choices for these answers are going to be incidence rate, point prevalence rate, and the attack rate, right? So this is going to be our concept check. So which one of these would be the incidence rate? 1, 2, or 3? Okay, so everyone's putting 1, which is correct. So the incidence rate equals the number of new cases of a disease for a specified time period divided by the population at risk for the same time period multiplied by a constant. Okay, now which one would be the point prevalence rate? correct. Our point prevalence rate is the proportion of persons in a population with a particular disease or attribute at a specific point in time or over a specified time period. The way that I always that the point prevalence rate, the way I remember it, because it helps me to remember it, is we've been dealing with an outbreak for quite some time, and we conduct PPSs, so point prevalence surveys, and it always just helps me to remember that it's a specific population with a particular disease at a specific point in time. So when we conduct a point prevalence survey at a facility, for example, with rectal screenings, we're getting all of that population in that specific nursing home or LTAC or hospital at a very like specific and particular point in time. So that's how it helps me remember. As I've told you guys before, statistics isn't my strongest. I'm not the strongest in statistics, so I have to come up with different ways to help me remember some of these things, and some of them may be silly, but I'm just letting you know what works for me. And then last, we have our attack rate. So the attack rate is the proportion of persons at risk who become infected over an entire period of exposure, or a measure of the risk or probability of becoming a case. So those are basically definitions that you should know, but it's not as important to know like the specific definition as it is to understand what you're looking for when you're trying to find the incidence rate or the point prevalence rate or an attack rate, if that makes sense. So let's do an example. So the incidence rate equals the number of new cases of a disease for a specified time period divided by the population at risk for the same time period multiplied by a constant. So our example is during 2011, 840 patients in Hospital A developed urinary tract infections. The hospital had 45,628 total patient days for the year. What is the annual incidence rate of UTIs per 1,000 patient days? Right? Okay, so I'm gonna give you guys a second to go over this. So we have two answers so far. I'll go ahead and give you guys another couple seconds to work it out. Okay, so we had a lot of people getting this correct. Actually, everyone who answered it got it correct. Everyone had 18.4, 18.41. So that's great. That means that you guys are understanding how this concept is working, which is okay. That is awesome. So okay. So I feel I don't need to go over this one. Everyone got it correct. But it's pretty much described here that the incidence rate is going to be 840, which is going to be your patients, divided by 45,628, which are the total patient days for the year, times the annual incidence per 1,000 patient days, and 1,000 is going to be our constant. So there we go. Very good. All right, question 2. All of the 72 patients in a chronic hemodialysis center were tested for hepatitis C virus, HCV. 8 of the patients were identified as HCV positive. During the following year, 2 of the dialysis center's patients who previously tested negative for HCV converted to HCV positive. What was the incidence rate for the year? Okay, so let me give you guys a hint. So the hint is you're going to be tempted to divide 2 by 72. However, that's incorrect. You need to think critically about what they are asking you, right? So remember what those values are. What would y be? I'll go ahead and give you guys another hint. So the incidence rate equals the number of new cases of a disease for a specified time period divided by the population at risk for the same time period multiplied by a constant. Okay, so let's go over this. So the numerator in this scenario is 2 because that's our number of new cases. The denominator would be the patients who are at risk for developing HCV. So our problem tells us that all 72 patients in a chronic hemodialysis were tested. 8 of the patients were identified as HCV positive. So if they already have HCV positive, they cannot be a part of our at-risk population. So that brings it down to 64. So if we do 2 divided by 64 times 100, we're going to get 3.1, which is what the majority of you guys selected. So very good, but that's an example of how they might trick you because you think it's a straightforward question, right? You think that it's a straightforward question that you're just going to go ahead and divide 2 by 72. However, you need to remember that your denominator is going to be your at-risk population. If those people are already positive for hepatitis C, they are not considered to be at risk. They already have the disease that cannot be included in the denominator. Does that make sense for everyone? Okay, perfect. They're gonna find ways to try to trick you guys when you're taking the exam. And that's okay because you're better and you're smarter than them. So it's gonna be fine. We just have to basically learn what our strategies are when you're taking the exam to make sure that you don't fall into the traps that they're placing throughout the test. Okay, so question 3, true or false? The prevalent double rate. The prevalence rate only includes new cases that developed within the surveillance time period, whereas the incidence rate includes all cases present during the surveillance period, regardless of the onset date. Okay, yes, this one was an easy one. Very well. Good job, guys. Yes, that's correct. So, it is the opposite, right? It is false. So the incidence rate is going to include our new cases that develop within the surveillance time period, whereas the prevalence rate is going to include all cases present during the surveillance period, regardless of the onset date. All right, let's move over to the attack rate. So the attack rate is going to be usually expressed as a percentage and is used almost exclusively for epidemics or outbreaks of disease where a specific population is exposed to a disease for a limited time period, right? So it's for a very specific time period. The attack rate is going to equal the number of new cases of disease for our specified time period divided by the population at risk for the same time period multiplied by 100, right? Because once again, our attack rate is usually expressed as a percentage. The attack rate is the same as the incidence rate, except that the attack rates are always expressed as cases per 100 populations or as a percentage, right? So that is the difference. So let's do a concept check. During the month of February, the IP finds that there were 3 sternal wound infections among patients undergoing coronary artery bypass grafts or CABG. Dr. A performed 28 surgeries, Dr. B performed 26 surgeries, and Dr. C performed 6 surgeries. What was the surgical site infection attack rate for CABGs in February? Take out your phones. If you need to, use your computer calculator. Whatever helps you. You will have access to a calculator during the test. Okay, so we got the majority of our responses, which are correct. 5%. Very good. Everyone got 5%. So that is wonderful. So in this example, right, this basically goes over the definition of an attack rate once again. But in our example, the numerator was going to be 3, which was the number of new cases, right? The number of new infections or surgical site infections. What was it? Sternal wound infections. So that's our numerator, 3. The denominator is a total number of CABGs performed. So the people at risk who could have gotten these sternal wounds are the people who were operated on. So that's going to be a total of 60. So 3 divided by 60 times 100 is going to give us our correct answer, which will be 5%. So question 4. 15 persons were infected with salmonella at a picnic where 75 ate egg salad sandwiches. Surprise. What was the attack rate, not attach rate? What was the attack rate of salmonella among those who ate the egg salad sandwiches? And those are our options. And once again, our attack rate's the number of new cases divided by the population at risk for the same time period. So, correct. Correct. The answer is D. Very well done, guys. You guys are doing really well on all these questions. That's exciting. So the mortality rate, let's quickly go through the mortality rate. You may have questions on this, you may not. It's part of chapter 13, and I just recommend that you guys have a really good grasp on all of the different concepts in chapter 13. It's a pretty important chapter for the exam. I know I've said that probably like 500 times, but I'm saying it for a reason. So let's go over mortality rate. So mortality rate is a measure of the frequency of death in a defined population during a specified time, usually a year. The crude mortality rate measures the proportion of the population dying each year from all causes. So crude mortality rate measures the proportion of the population dying each year from all causes. And then the cause-specific mortality rate measures mortality from a specified cause for a population. So our mortality rate equation is going to be x divided by y times k, and x is going to be the number of people in a defined population during a specified interval of time who, 1, die of any cause, which would be the crude rate, or 2, die of a specified cause-specific rate. Y is our estimated population, and K is usually an assigned value of 1,000 when calculating crude rates, and 100,000 is used for cause-specific rates. This right here, K is what will mess you up on the exam. K is what will mess you up on the exam because you're so used to using 1,000 repeatedly all the time. When you're dealing with CAUTIs, when you're dealing with CLABSIs, and you're like, yeah, it's 1,000, it's 1,000. You need to remember that it's 1,000 when you're calculating crude rates, but 100,000 when you're using cause-specific rates, right? You got to know it, because if they ask you for a crude mortality or a cost specific and you don't know what you need to use as K, that's going to completely throw off your answer. And I guarantee you that they'll have that answer using 1,000 as one of your answer choices. Guaranteed. If you do like a cost specific rates, they'll have that answer because they are expecting for you to make that mistake. So let's do example 2. In a city with a population of 250,000, 2,106 persons died during the year. 12 persons died of bacterial meningitis. What is the crude mortality rate per 1,000, and what is the cause-specific rate per 100,000? So let's do the crude mortality rate, right? Which is going to be the whole thing, the whole pot, the whole enchilada. Everyone dying from everything. So let me give you guys a minute to do that. Okay, very good. So that is correct. We're using the 1,000 value because it's the whole enchilada. We're doing everything. So our crude mortality rate is 2,106 divided by 250,000 times 1,000. Now let's do the cause-specific mortality rate. And for cause-specific, remember your denominator, I'm sorry, your constant that you're going to multiply by is 100,000. And you're focused specifically on one cause. Stephanie, you are just unstoppable today. You've been answering everything so quickly. I can't even handle you today. You go, queen. Okay, so very good. Awesome. You guys all got it correct. Perfect. So when you're taking your practice questions, you're going to have a question on crude mortality rate or cost-specific mortality rate. I can't remember, and you'll be ready to answer that. Now, let's do an overview of the standardized infection ratio. For our IPs on the call, I know this is a piece of cake for you guys. You're dealing with SIRs all the time. Um, but for EPIs, we don't necessarily deal with standardized infection ratios ever. So it's important for us to become familiar with some of this terminology. And of course, you're not gonna totally understand everything in one lesson, but at least we can review it. So the standardized infection ratio. So a standardized infection ratio is a summary measure that compares HAI rates over time among one or more groups of patients to that of a standard population. SIRs are calculated by NHSN, and each SIR is procedure specific and based on specific patient risk factors. The analytical concept is the same as standardized mortality ratio. So it compares how a single healthcare facility's infection rates differ from a national standard. An SIR can only be calculated if the expected number of infections is one or more, and the calculation formula is the observed number of infections divided by the expected number of infections. So I do see that we have one. Okay, Cheryl from Florida Hospitals on the call. Cheryl, you can answer in the question box. Would you feel comfortable just talking to us about how you deal with the SIR, the SIR, like just on a daily basis or on a regular basis, like what, just so you can maybe try to explain it to us, or how you use it in healthcare at your facility, since you're one of the IPs on the call? Would that be okay? Let me see if I can unmute you. Okay.
Before, like, you just hand off like a urine culture. It's like, here's a urine culture. You need to evaluate it. What do you think?
Okay. Okay,
It
Cheryl.
doesn't bother me that much to like work something up when it's finals because it's like at that point the patient's like done on your unit. Like,
Yeah, I like doing it when it's final because everything is kind of like there, like they've documented whatever it is that they're going to document for it.
I don't know. Yeah. Maybe we do need to just involve Jackie in the conversation because we might have other insight.
Cheryl, can you hear us?
Because I know with this one, I did check there is a Foley in place.
Okay, so I don't think Cheryl can hear us, but let's move on then. Okay, so the interpretation of an SIR. So the SIR of 1, the facility's rates are the same as that expected by the NHSN benchmark. An SIR greater than 1, the facility rates are higher than the NHSN benchmark. And then an SIR of less than 1, the facility rates are better than the NHSN benchmark. So the National Healthcare and Safety Network is what infection prevention is utilized to report all of their HAIs, whether it's a CLABSI, whether it's a CAUTI. And so this is where you're going to be dealing with the standardized infection ratio. We as EPIs, I mean, we don't utilize NHSN, and I would recommend, if you don't know anything about NHSN, there's a great video that the CDC does trainings every year on NHSN, and there's just a basic one of definitions. I'll send that out via email because it might be helpful for you just to become familiar. If you're an experienced IP, you definitely don't need to do that. But if if you're not familiar with it at all, I would recommend it. So let's talk about the relative risk or the risk ratio. So the relative risk is a measure of the strength of association used in prospective and experimental studies. It's the probability of developing a disease if the risk factor is present divided by the probability of developing disease if the risk factor is not present. It's sometimes called the risk ratio or the ratio of the two incidence rates, and it estimates how much more likely disease is to occur in exposed groups compared with unexposed ones. It's used for cohort studies. It's used as prospective, and it starts at a point of 0 and continues into the future. And it asks the question, what is the risk of developing disease if exposed to the risk factor, right? So if you're dealing with an outbreak in your facility and you have all of these patients that keep getting an infection, whether it's, I'll just do Pseudomonas because why not? You guys know how I feel about Pseudomonas. So they keep getting a Pseudomonas infection, and you're trying to get to the bottom of, well, what is the risk of them developing this infection if they have a trach, if they're vented, if they're getting dialysis? So this is how you're coming up with your risk ratios. You're really asking, what is the risk of developing disease if exposed to this risk factor? Which could be a multitude of things. It could be, are they getting compounded medication from the pharmacy? Like, you have a variety of risk factors, and you would come up with that by doing your thorough medical record extractions, but that's kind of where the relative risk is going. Now, interpreting the risk ratio, if the risk ratio is equal to 1, there's really no significant association. If the risk ratio is greater than 1, then there is a positive association, meaning a worse outcome. And if the risk ratio is less than 1, there is a negative association, meaning that it is protective. So they'll find ways to ask you about risk ratios, and usually you're thinking, oh, if the number is higher, if it's positive, this is going to be, a good thing. And so you need to remember, risk ratio is trying to assess the possibility of this patient getting a disease if they're exposed to, or if they have this certain risk factor. So if the risk factor is greater than 1, that is going to involve a worse outcome. And that's what you need to remember when you're answering these questions about risk ratios. Now, with odds ratios, this is another measure of association that's closely related to the relative risk. It's the probability of having a particular risk factor if a condition or disease is present, divided by the probability of having the risk factor if the disease or condition is not present. It is used for all types of studies with nominal data, but is used most for retrospective and cross-sectional studies. Were any of you guys able to watch the YouTube video that I sent out on the different types of studies? Did you guys find that helpful? I don't know if any of you watched it. I know some of you did. Yeah, okay, good, because you want to be kind of reading through this, and you don't just want to be nodding along. You want to be thinking, oh, yes, okay, that makes sense. You're able to think what a cross-sectional study is as you're reading through the text, because if you don't, it can be harder to understand these concepts. So the odds ratio is sometimes called the cross product ratio or the relative odds. The odds ratio is used with case control studies, which begin with subjects who already have the disease and compare with those who do not have the disease. The odds ratio is retrospective. The disease is already present, and it looks at prevalence. So it's not really appropriate to use with chronic diseases. And it also asks the question, if the disease is present, what is the likelihood of having been exposed to the risk factor? Now, correlation. You will have a question on correlation. It may just be 1, it could be 2, but this is just important to understand. So correlation is used to calculate the direction and magnitude of a relationship between 2 variables. Correlation calculates a value r, little r, lowercase r, which measures the degree of the relationship. The calculated range values can reach between +1 and -1. The closer r is to 1, the stronger the relationship. A positive correlation exists when one variable increases, so does the other. So our example would be, the longer a urinary catheter is in place, the greater the risk of developing a UTI. So that would have a correlation closer, right, to 1, because it has a stronger relationship. And remember, the calculated values only range between +1 and -1. A negative correlation occurs when, as one variable increases, the other increases. So you have an increase in hand washing, which is going to result in fewer infections. And then lastly, as R gets closer to 0, the less the association between the two variables. With a value of 0, there's really no correlation. So let's touch a little bit on sampling distribution. So inferential statistics assumes some type of sampling distribution, whether it's normal or skewed, against which the observed data from sampling are compared. Statistical inference based on the normal distribution, sometimes referred to as the bell-shaped curve, is the type most frequently encountered in the literature. So bell-shaped curve, remember that's our normal distribution. We looked at that last week. In the day-to-day surveillance and data collection conducted by infection preventionists, the sample sizes or number of infections are usually small and a normal distribution cannot be assumed, right? Once your sample size is getting larger and larger, the closer that you're going to get to a normal distribution, right? So if your sample size is small, you can't really assume that it has a normal distribution. And that's going to come into play when you're deciding what kind of statistical tests you're going to utilize. But just remember that smaller sample size, you can't assume a normal distribution. As the sample size gets larger, you can assume a normal distribution. Okay. So let's go over hypothesis testing. And so this is where we are going to, did everyone get the opportunity to watch the video on the p-value? If you did not, we're going to watch that one because it's very great, but I want to know if you guys were able to watch it. Okay, so we have some no's, we have some yeses. All right, well, let's watch the one on type 1 and type 2 errors first. I guess, okay, let's do this slide first. Hypothesis testing. So a common use of statistics is hypothesis testing. And you're basically, it's a statement of expected results. Hypothesis testing uses the distribution of a known area in the normal curve, and it estimates the likelihood or probability that a result did not occur by chance, right? Estimates the likelihood that a result did not occur by chance. First, a research or alternate hypothesis is formulated. The hypothesis states the expectation to be tested. For example, Dr. A has a higher surgical site infection rate than does Dr. B, and then a statement that is opposite to the research or alternate hypothesis is developed, like Dr. A has a lower infection rate than Dr. B does, right? The latter is called the null hypothesis. And which is depicted as HO. In the video, he refers it to the ho and the ha. So the ho is always stated to be rejected. The research or alternate hypothesis is the desired result. Only two outcomes are possible with hypothesis testing. Either the null hypothesis is accepted or the null hypothesis is rejected. So let's get into this video here. Where's my my mouse? There it is. Okay. Okay. All right, let me know if you guys can hear it.
What we're going to do in this video is talk about type 1 errors and type 2 errors. And this is in the context of significance testing. So just as a little bit of review, in order to do a significance test, we first come up with a null and an alternative hypothesis. And we'll do this on some population in question. These will say some hypotheses about a true parameter for this population. And the null hypothesis tends to be kind of what was always assumed or the status quo, while the alternative hypothesis, hey, there's news here. There's something alternative here. And to test it, and we're really testing the null hypothesis. We're going to decide whether we want to reject or fail to reject the null hypothesis. We take a sample. We take a sample from this population. Using that sample, we calculate a statistic we calculate a statistic that's trying to estimate the parameter in question. And then using that statistic, we try to come up with the probability of getting that statistic, that we just calculated from that sample of a certain size, given if we were to assume that our null hypothesis, is true. And if this probability, which is often known as a p-value, is below some threshold that we set ahead of time, which is known as the significance level, then we reject the null hypothesis. Let me write this down. So this right over here, this is our p-value. This should all be review. We introduced it in other videos. We have seen in other videos if our p-value is less than our significance level, then we reject our null hypothesis. And if our p-value is greater than or equal to our significance level, alpha, then we fail to reject our null hypothesis. And when we reject our null hypothesis, some people say that might suggest the alternative hypothesis. And the reason why this makes sense is if the probability of getting this statistic from a sample of a certain size, if we assume that the null hypothesis is true, is reasonably low, if it's below a threshold, maybe this threshold is 5%. If the probability of that happening was less than 5%, then hey, maybe it's reasonable to reject it. But we might be wrong in either of these scenarios, and that's where these errors come into play. Let's make a grid to make this clear. So there's the reality. Let me put reality up here. So the reality is there's two possible scenarios in reality. One is that the null hypothesis is true, and the other is that the null hypothesis is false. And then based on our significance test, there's two things that we might do. We might reject the null hypothesis, or we might fail to reject the null hypothesis. And so let's put a little grid here to think about the different combinations, the different scenarios here. So in a scenario where the null hypothesis is true, but we reject it, that feels like an error. We shouldn't reject something that is true, and that indeed is a type 1 error. Type 1 error. You shouldn't reject the null hypothesis if it was true. And you can even figure out what is the probability of getting a type 1 error? Well, that's going to be your significance level. Because if your null hypothesis is true, let's say that your significance level is 5%. Well, 5% of the time, even if your null hypothesis is true, you're going to get a statistic that's going to make you reject the null hypothesis. So one way to think about the probability of a type 1 error is your significance level. Now, if your null hypothesis is true and you fail to reject it, well, that's good. We could write this as, this is a correct conclusion. The good thing just happened to happen this time. Now, if your null hypothesis is false and you reject it, that's also good. That is the correct conclusion. But if your null hypothesis is false and you fail to reject it, well, then that is a type 2 error. That is a type 2 error. Now, with this context, in the next few videos, we will actually do some examples where we try to identify, one, whether an error is occurring and whether that error is a type 1 or a type 2.
Okay. So that gives you a pretty good overview. Cancel. Relax. Okay, so that gives you a pretty good...
Say that I run a website that currently...
Okay. So that gives you a pretty good idea of basically type 1 and type 2 errors. So I hope that video was helpful. When I was studying for my exam, I watched a lot of videos on YouTube, like a ton of videos on YouTube on concepts that I didn't understand. That's how I found the p-value video, and it really helped to click the information, because I did my MPH focusing on global communicable diseases. I didn't focus specifically on epidemiology, so I don't have as great of a background with statistics as some of my other colleagues do. But watching videos and trying to find ways to really understand the information will really help you when you're taking your exam. So for type 1 error and type 2 errors, a type 1 error means that you're rejecting the null when it is true and attributing significance when there's none, and that the probability of committing a type 1 error is referred to as the significance level, and alpha is always stated. A type 2 error means accepting the null hypothesis when it is false or not attributing significance when it does exist. And this is a different interpretation or a different way of basically saying what Khan Academy just did on their video. It's just a different chart displaying the same information. So let's do a concept check. If the null hypothesis is false, you cannot make which kind of error? If the null hypothesis is false, you cannot make which kind of error, type 1 or type 2? I've only had 2 people answer so far, so that lets me know you guys are thinking. If the null hypothesis is false, you cannot make which kind of error? Okay, well, when you have a type 1 error, what are you doing? You are rejecting the null when it is true, right? So the correct answer is type 1. You cannot make a type 1 error. A type 1 error occurs when a significant test results in the rejection of a true null hypothesis. So if it's false, you cannot commit a type 1 error. A type 1 error is only committed when your null is true. Does that make sense? And of course, they're not gonna, they may not ask you a question specifically like this one, but do you see how understanding the concept behind the type 1 and type 2 error can be applicable to other examples, or how they'll be able to kind of use that to ask you other questions? I hope that makes sense. I know some of the questions are not specifically, like straight from the APIC text, but I do them so that it gets you thinking. So the next question is, which of the following best describes a type 1 error? Which of the following best describes a type 1 error? Okay. All right. So let's go back. So a type 1 error means rejecting the null when it is true and attributing significance when there is none, right? So you are basically saying that you reject the null. We don't believe in the null, even though the null is the correct answer. So the correct answer for this one is going to be that the null is true, but we mistakenly rejected. It's not that we failed to reject it, it's that we mistakenly reject it, or we reject it. Do you see why she's putting but we mistakenly rejected? Because it's pointing to the fact that it's a type 1 error. So most of you got this one right, but we did have a couple people putting B as the answer. So it just at least I knew you guys knew that the null is true, so you can narrow it down to B or D, which is great. But remember, you reject the null when it's true. Type 1 error. Okay, another concept checked. This is for, I'm hoping you guys watch the video. So the p-value, what does the p-value tell us? A, the probability of getting unusual results. B, the probability that the null is true. C, the probability that the null is false. And D, the probability of getting the expected results. Mm. Okay. Remember during the video when he was talking about the p-value as it gets lower, it gets more peculiar? Remember him utilizing that word, peculiar, when he was describing the p-value in the video that we sent out? So the p-value is really trying to help you to assess the probability of getting unusual results. Okay? That's a great video to watch. I may just play it at the end of this um, because I watched it multiple times. All right, so we have a question here. What is the probability of committing a type 1 error if the p-value is 0.10? 0.10. A, 1 in 100, B, 1 in 5, C, 1 in 10, D, 1 in 20. Okay, we have some people guessing. Some people saying they don't know. That's okay. That's okay. This is why we do these questions. This one's actually from the APIC text. So the correct answer is 1 in 10. So let's read through the rationale. In statistical hypothesis testing, type 1 and type 2 errors refer respectively to incorrectly rejecting a true null hypothesis or incorrectly failing to reject a false null hypothesis. The first kind of error that is possible involves the rejection of a null hypothesis that is actually true. This kind of error is a type 1 error. Type 1 errors are equivalent to false positives. Type 1 errors can be controlled. The value of alpha, which is related to the level of significance that we selected, has a direct bearing on type 1 errors. Alpha is the maximum probability that we have a type error. For a 90% confidence level, the value of alpha is 0.10. This means that there is a 10% probability that we will reject a true null hypothesis. In the long run, 1 out of every 10 hypothesis tests that we perform at this level will result in a type 1 error. Okay, if chance is a likely explanation for the difference between a sample statistic and the corresponding null hypothesis population value, then A, the difference is not statistically significant, B, the difference is statistically significant, C, the null hypothesis can be rejected, and D, the sample result is not compatible with the null hypothesis. If chance is a likely explanation for the difference between a sample statistic and the corresponding null hypothesis population value, then what is the correct answer? Now, I want you to think about when he was referring to the trick coin, right? That should help you get to the correct answer. Okay. So we have some C's, we have some A's, and that's basically the two answer choices that we have, C and A. The correct answer is that the difference is not statistically significant, right? So if chance is a likely explanation, right, does that mean that there could possibly be a trick coin involved or that it's an actual regular coin? When we're relating, I feel like the majority of you watched the video. Exactly, Stephanie. Yes, it's a regular coin. So our difference is not going to be statistically significant. Now let's read through the rationale. Statistically significant refers to the likelihood that a result or relationship is caused by something other than mere random chance. Statistical hypothesis testing is traditionally employed to determine if a result is statistically significant or not. This provides a p-value, representing the probability that random chance could explain the result. The p-value is representing the probability that random chance could explain the result. In general, a 5% or lower p-value is considered to be statistically significant. If chance is a likely explanation, then the study is not statistically significant. Does that make sense? Does that rationale make sense? And you can say, yes, it makes sense. No, I totally don't get it. I don't know what you're talking about. I don't know what the p-value is. I'm completely lost. That's totally fine. But does that answer make sense to you guys? Okay, so most people are saying yes, it does make sense. Okay, good. I know. I know. It I know. It's not fun, but we got to do it. So some chapter 13 questions. True or false? As the sample size increases in number, the effects of the random influences are diminished and the data get closer to a normal distribution. Is this true or false? True or false? True or false? If you have a smaller sample size, there's more likelihood of that distribution being skewed. If you have a larger sample size, you're going to be getting closer and closer to a normal distribution. All right. The device utilization ratio for a facility that has 600 ventilator days and 3,000 patient days is the device utilization ratio for a facility that has 600 ventilator days and 3,000 patient days is Whew, we have like every answer choice up on the board right now. We have A, B, C, and D. Okay, be honest. Are any of you guys guessing the answer? You can say yes. Okay, we have some guessers. That's okay. That's okay. I know. I know. We gotta, it's just practice. You gotta practice. You gotta drill this stuff. Don't worry. There's time. There is time. We are only on week 7, guys. Don't worry. And this stuff will come up over and over again. So don't be concerned. So the device utilization ratio is the proportion of patient days for which a certain device is used. Device utilization ratios are specific to that device, such as a central line, a catheter, or ventilator. Device utilization ratios reflect the amount of devices used, and it is a reflection of the patient's severity. The formula is the number of device days divided by the number of patient days. In this example, we would calculate it as 600 divided by 3,000, which equals 0.2. And Deborah Dice says, I report this every month to my committee. Great. Right. So some of these are for RIPs, they're going to be much easier because it's things that they're dealing with all the time. For us EPIs, we don't deal with device utilization ratios. And so this is where you need to, take advantage of what you're really good at and what your strengths are, and then pay attention to those things that are going to be the weaknesses, because that's what's going to make or break your test score. So good. Deborah, you did great. You got that one right. Okay. So another question. The Employee Health Service has notified the infection preventionists that 7 employees have Pseudomonas aeruginosa folliculitis. Shout out to Pseudomonas. Initial investigation reveals that 6 of the 7 cases belong to the same health club. Working on the hypothesis that the whirlpool at the health club is associated with infections, the IP has decided to conduct a case control study using 2 controls for each case. Which of the following groups is the most appropriate control? I'm going to let this one marinate. Give you guys some time. Right. So, working on the hypothesis that the whirlpool at the health club is associated with the infections, the IP has decided to conduct a case control study. So, we are trying to basically look at the whirlpool at the health club, right? That is a key part of what we're looking at. You guys are going back. Francis, stop changing your answer. Francis keeps changing her answers. Okay, right. So, non-ill hospital employees matched for age and sex. Is that really going to help us when it comes to basically working on the hypothesis that the whirlpool at the health club is associated? Mm. Hospitalized patients with skin disease matched for age and sex. Well, these hospitalized patients may or may not have gone to the health club, right? So goodbye. Non-ill family members of the ill employees. Guarantee you the non-ill family members are not going to the health club and utilizing the whirlpool, not whirlpool. What's going on with me today? Okay. So our correct answer is non-ill members of the health club matched for age and sex. The choice of appropriate controls is central to the validity of results in case control studies. The goal is to choose controls that are representative of the study base with respect to the exposure. The source of controls is dependent on the source of cases. In order to minimize bias, controls should be selected to be a representative sample of the population that produced the cases. In this example, non-ill members of the health club would have the same exposures as the cases. Age and sex are often used as matching variables because they are usually strong confounders. All right. Oh, Luce, you just are the worst. Okay, so let's go over it anyway. So the local health department nurse the local health department nurse has asked you to help her develop a graph to display the number of cases of tuberculosis in your state. The trend has been increasing and she wants this to be dramatically shown in the graph. The best graph for this would be a histogram. Why is the histogram? So we know histogram is the correct answer because I clicked on the thingy too much. But can someone explain to me why the histogram is going to be the best at dramatically showing this? Chapter 13. You're wondering, this has nothing to do with p-values. I know, but it is on chapter 13. Okay, crickets. So let's look over, wait. Let's look over the rationale. A histogram is a graphic presentation of data. While the same information can be presented in tabular format, a histogram makes it easier to identify different data, the frequency of its occurrence, and categories. Its advantage is that it not only clearly shows the largest and smallest categories, but also gives an immediate impression of the distribution of the data. All right. So our next question is sensitivity. This is from the Measures of Validity paper. Sensitivity may be defined as, not reading all of these, A, B, C, or D. Okay, so we have some A's, some C's, another A, Okay, so when we're looking at sensitivity, right from the beginning, you should be able to cross one out, right? Because when we're looking for sensitivity, we are really trying to detect true positives. So we can go ahead and get rid of this one, right? B. Now let's look at some of the difference. So this one's saying with, this one is saying without, and this one is saying without. So based on that, based on you highlighting those keywords, does that help you get to the answer? And it should be a yes. It should help you. When you're taking this test, yes, you need to know the information, but don't get frazzled if right off the bat the answer does not, jump out of the screen to you, because it is a computer-based test. So if it doesn't jump out of the screen, just take a big deep breath and ask yourself, what do I know? Right? So we can get rid of B. And now we're looking at, okay, our other options are A, C, and D. The correct answer is going to be A, because when you're dealing with sensitivity, it's the ability of a test to detect true positives, so persons who actually have the disease, when applied to a population with the disease. So if you know your definitions and if you know how sensitivity is utilized when it comes to laboratory testing, sensitivity and specificity, that will help to guide you to the correct answer, specifically since C and D are saying without the disease, which should be a key, in letting you know those are not the correct answers. Okay, this is our last question. What is the positive predictive value of the following data? And this is once again dealing with the measures of validity paper that I sent out. So Melissa said, I think of a UA and the culture and sensitivity. So that's in relation to the previous one. Okay, so what is the positive predictive value of the following data? Okay, so let's start working through this. So the positive predictive value is the proportion of people with a positive test result who have the disease. And the equation for the positive predictive value is going to equal true positives divided by true positives plus false positives. So our true positives is going to be 100 because these are the people who actually have the disease, right? They actually have the disease and their test result was positive. So that's our true positive. Our false positives are going to be 3. The result was positive, however, they do not have the disease, right? So now that we have those, those values, you should be able to plug and chug into the equation to get the correct answer. Since we only had 3 people answer, I'm assuming that this is something that, the majority of you may not feel super comfortable with, but with that help, you should be able to get to the correct answer, which is going to be 97%. And they'll have charts and they'll have graphs for you when you're taking your exam, and they'll also have a calculator available. Well, so the last part of today, what I'm going to go ahead and do is, how do I get out of here? What I'm going to go ahead and do is just play the p-value video for those of you who did not get the opportunity to watch it. If you did, feel free to log off and have a wonderful Wednesday. However, if you didn't, I would highly suggest that you stay on and, watch this video so that it can help you understand the p-value. All right, so let's full screen this. Yeah, I've seen this video a couple of times. Okay.
Back here hopefully to help you guys understand this thing called p-value. We're looking at this thing. What is a p-value? I know it's a puzzle. What is this thing? I've been interpreting it, but I don't quite understand. You're going to keep interpreting this thing, so it's real important you have this thing down, okay? You're going to be, at the end of your report, you're going to write something like, with a p-value so low, I reject the null. There's strong evidence that people prefer Parmesan cheese in their meatballs, not Romano. Whatever you do, you need to know what this thing is. So when you write a conclusion, you interpret the p-value, you know what you're saying, okay? So hopefully this quick example will help you understand. All right, so I got a coin here. Here's my coin, okay? All right, and you're going to say, all right, we generally make a null and an alternative hypothesis. A ho and a ha, that's what I say. Make a ho and a ha. Ho, ha, make your null. Your null hypothesis is always the nothing weird's going on hypothesis. It's like the boring hypothesis, the no trickery, the Nystrom's not a magician hypothesis. So we're going to talk about this coin. We're going to say it's a fair coin. And my null hypothesis is that everything's hunky-dory, fair coin. Okay? The alternative hypothesis is that there's some trickery going on. There's something weird. There's something trickery. I don't even know if that's a real word. Yeah, maybe it is. So
What did I do? Oh goodness. Sorry guys. I don't know what I did here.
something weird. There's something trickery. I don't even know if that's a real word. Yeah, maybe it is. So it opposes this. This is saying, oh, the coin's fair. This is saying there's some trickery going on. Nice just being silly. It's a trick coin. But you're not going to go with the trick coin until you have enough evidence. So that's kind of like this whole null alternative thing is you go with this, oh, it's a fair coin. You just assume things are okay until you're like, whoa, what is that? And that p-value is the, whoa, what is that? The p-value is like the peculiar, that was peculiar. So you think about, wow, that's really peculiar. Oh, that's like a really low p-value and something's like really weird. You weren't expecting it to happen randomly. That's the low p-value. So we're going to see what happens here. Here we go. I flip a coin. Tails. It's tails. So here's our observation, and then I'll put a p-value here. And what happened, I observed one tail. Now here's the question. Do you think that this is a trick coin? Is it trick coin? Is there some trickery going on, or do you think it's a fair coin? You're probably saying, I don't have enough information. Well, you do. Here's your information. Every single time I flipped it, it landed on tails. But what you're going to say is, oh, if the null were true, if that was a fair coin, if it were a fair coin, that happens half the time, man. I'm not convinced it's a trick coin right now. I don't think there's any trickery going on, and that's good reasoning. But that's what that p-value is. It's the likelihood of this thing occurring if this null were true, if it were a fair coin. Okay? I flip it again. Whoa. Oh, look at that! Tails again! I can't believe it. So, tails twice. Two tails. Now do you believe that it's a trick coin? Do you believe something trickery is going on? You'll say, no, man, that'll happen like this happens about half the time. This happens about 1 out of every 4 times you flip a coin twice. So it's about a 0.25 p-value. Now notice, think about this. The p-value is the likelihood of what you saw happening if the null were true, if it were a fair coin. Because if this were a trick coin, meaning a two-tailed, tails on both sides, how often would you see 2 tails in a row? All the time. Okay? So the p-value is assuming that it's a fair coin. It's assuming the null is true. Let's see. I'm going to do it again. You're going to catch it. Tails again. Can you believe tails again? I can't believe there's 3 tails in a row. And in my class, when I'm doing this, I'll say, does anybody think this is a trick coin? And everyone will be like this. So then I'll flip it again. And this happens about 12.5% of the time. Flip it again. Oh, man, I'm horrible at this. Oh, my goodness, but it happened to land right on tails again. Look at this. Tails again. So we see 4 tails in a row, and that happens randomly about 6% of the time. And after the 4th tail, you'll see heads like, churning. It's great when students are doing that. They're actually thinking. They're like, well, this is kind of weird. Good. You're saying that's peculiar. That's your p-value. Okay. Notice what's happening to the p. It went from 0.50, 0.25. It's getting lower. Notice as the p-value gets low, it starts getting more peculiar. And this is when I say, do you think this is a trick coin? Do you think I'm up to something? This is when students, you'll see a hand go up. I think you're up to something. I'll say, I like your reasoning. And I'll do it again. 5 tails. 5 tails in a row. That happens about 3% of the time with a fair coin. That 5th tail, you start seeing, people start saying, I think that's weird. Then I do it again. The 6 tails, which only happens about 1% of the, 1.5% of the time, whatever. Everyone's going, okay, that's weird. Now, the deal is, yes, it's a 2-tailed coin, okay? You buy a 2-tailed coin at a magic shop, and it is trickery. There's definitely some trickery, okay? I never, ever show it. I will not show the 2-tailed coin. Because in hypothesis testing, you never really know. You just have to go with your gut. But the importance is just notice naturally what kind of happens. You start feeling, and everybody that starts, when you start seeing something right around this area, right around here, this is what the hands up, I think it's weird thing. And that happens when the p-value falls below 0.05. When the p-value gets below 0.05, that's when you start getting a little sour feeling, and you're like, oh, it's weird, it's a little strange, I don't get it. Ooh, that's natural. Think about a card trick. What p-value makes you go, whoa? It's like a wow factor. If I give you cards and I'm like, here, pick a card, and you pull up a card and you're like, and I say, that's a red card. You're not going to be like, oh my God. Oh my God, he gets my card. That's not you're not wowed with a red card. But if I'm like, oh, it's a heart, that's a little more of a wow factor, but you're probably not going to hire me as a magician at your cousin's birthday party, right? So what do you need to see in order for a card trick to be like, wow? I need to shuffle them around. I need to shuffle them around and let you hand you one and say, dude, you've got the King of Hearts. And that's when you're like, wow, he guessed the King of Hearts. Now, the p-value of that, the likelihood of me just guessing that randomly, if there was no trickery, is 1 in 52. That's like a 0.02. That's like a 2% chance. That's a low p-value. So look what happens. The thing starts getting low. When the p-value gets low, you start guessing whether or not it's a fair coin, right? Because that's what people say. I know a magic trick. The first thing you think is like, yeah, prove it. Show me, please. Because you want the p-value to get low. So you can be like, oh, he's a magician, right? This is what's happening. Think of the logic behind the p-value. Just think about it. Notice what happened. If this were a fair coin, the likelihood of you seeing 5 tails in a row is so unlikely to happen randomly. It was so unlikely that you start wanting to go with the alternative. When the p-value gets low, when it's unlikely to have happened randomly, if the null were true, you start saying that was so unlikely to happen randomly. If the null were true, that I don't think it did happen randomly. I think the null's actually false. Basically, you're saying if the null were true, this is how likely it would happen randomly, which is wicked unrandom. I mean, it's unlikely. It's so unlikely to have happened randomly, you don't think it was random. Meaning, when you say that, you're saying it was so unlikely to happen randomly. If this were true, I don't think this is true. I think you've got a trick coin, and I do. I think you know a magic trick, there's some trickery, and it is. That's how hypothesis testing goes. So when you see and you interpret your p-value, make sure what you're saying is, it's the likelihood of this event occurring just randomly if the null were true. So when you say the p-value is low, I'm going to reject the null. You're saying it was so unlikely to have happened randomly if this were true that I don't believe it. You're starting to believe it's a trick coin. You're starting to raise your hand in class and be like, I think there's something fishy going on.
Okay. And then that's when you start thinking, man, that's weird. And it happens all the time. All this stuff you do. How do you think they prove like these big companies are causing cancer in the water supply? It's because it's unlikely that half the population of a small town just randomly going to get some sort of cancer, because you look at how it happens randomly and say that. If there was nothing fishy going on there, that's strange. It was like a 1 in a million chance of happening just randomly. That I don't think it was random. There's some serious pollution going on and someone's going to pay for it, okay? So you have to understand that the reason why we study randomness at all, and the reason why when you do your hypothesis tests and you have that randomness in there, you have to make sure there's something done randomly. We study randomness so we know how randomness happens, so we can say just this, that was so unlikely to have happened randomly that I don't think it was random at all. There was something weird going on, and I'm rejecting that null, and I'm going with the alternative, and so should you. Yeah.
So I love his video. It's so great. Just so you guys know, so our homework for this week is going to be the certification study guide, the 50 questions at the end of module 2. So if you could get started on that, that'd be great. All right, guys, that's all. That's it for today. I'll get this PowerPoint sent out and get the recording sent out. I hope you guys have a wonderful rest of your day. Bye.